The year was 1940, and the air above the English Channel smelled of salt, engine exhaust, and fear. At 38,000 feet, a formation of Messerschmitt Bf-109s cut through the thin atmosphere like a blade through silk. At that altitude, the cold was savage, minus 40 degrees. The pilots breathed through oxygen masks, their gloved hands resting on the control columns of the most feared fighter aircraft in Europe. They were fast, they were high, and they knew, with the confidence of men who had already crushed Poland, Denmark, Norway, and France, that nothing the British had could touch them up here. Below and behind them, the Heinkel HE-111 bombers droned toward London in heavy, pregnant rows loaded with high-explosive ordnance destined for the docks, the factories, and the civilian neighborhoods of a nation that was, for all practical purposes, fighting alone. The Bf-109 escorts had one job: get to London first, clear the sky of any British fighter foolish enough to climb to meet them. And for months, that job had been easy. Over France, the Luftwaffe had fought Spitfires and Hurricanes and found them wanting. The German pilots clocked the Spitfire at roughly 340 miles per hour. The Bf-109 could push past 380. In a dogfight, 40 miles per hour is not a gap, it is a death sentence. The British could not climb as high, they could not chase as fast, and in the brutal arithmetic of aerial combat, slower means dead. The Luftwaffe pilots had every reason to believe that the skies above Britain would be no different from the skies above Dunkirk. They were wrong. And the reason they were wrong had nothing to do with better pilots, better tactics, or better aircraft design. It had everything to do with a liquid. A clear, volatile, foul-smelling liquid that was being pumped into the fuel tanks of every Spitfire and Hurricane in fighter command. A liquid that did not exist in usable quantities anywhere on Earth just 5 years earlier. A liquid that a French war hero, an American daredevil, and a team of oil company chemists had pulled out of the periodic table through sheer stubbornness and desperation. This is the story of 100-octane aviation fuel, and it begins not in a cockpit, but in a laboratory. Not with a gun, but with a catalyst, and not with a soldier, but with a man who raced Bugattis. To understand why octane mattered, you have to understand what happened inside the cylinder of a Rolls-Royce Merlin engine at full power. The Merlin was the heart of the Spitfire. It was a masterpiece of British engineering, a supercharged V-12 that displaced 27 liters and produced over 1,000 horsepower. But all that power meant nothing if the fuel detonated at the wrong time. Inside each cylinder, a piston compressed a mixture of air and vaporized gasoline. At the precise moment of maximum compression, a spark plug fired, and the mixture ignited in a controlled burn that drove the piston down and turned the crankshaft. That was how an engine made power. But there was a monster hiding inside that process. If the fuel ignited too early before the spark plug fired, the result was called knock. It was not a gentle tap. It was a violent, uncontrolled explosion inside the cylinder that sent shock waves through the metal. Knock could crack pistons. It could shatter connecting rods. It could destroy a 1,200 horsepower engine in seconds. The octane rating of a fuel measured its resistance to knock. The higher the octane, the more you could compress the fuel-air mixture before it detonated on its own. And the more you could compress it, the more power you could extract from each stroke. It was pure thermodynamics. In the mid-1930s, every Air Force on Earth ran their fighters on 87-octane gasoline. It was cheap, it was plentiful, it was the same grade you could buy at a filling station for your Ford. And it imposed a hard ceiling on engine performance. At 87 octane, the Merlin could produce about 1,030 horsepower at a boost pressure of 6¼ pounds per square inch. If you tried to push it harder, the fuel would detonate prematurely and the engine would tear itself apart. Every aircraft designer in the world was trapped behind the same wall. You could build a better airframe, you could improve the supercharger, you could polish the propeller blades, but until someone gave you a fuel that could withstand higher compression without exploding, you were stuck.
Nobody seemed particularly concerned, except one man, and that man happened to be one of the most famous aviators alive. James Harold Doolittle had earned the first doctorate in aeronautical engineering ever awarded by the Massachusetts Institute of Technology. He had performed the first successful instrument-only flight in history, proving that a pilot could take off, navigate, and land without ever seeing the ground. He had set transcontinental speed records, he had won the Bendix Trophy, the Thompson Trophy, and had flown the notoriously lethal GBR-1 racer to a world speed record of 296 miles per hour. By 1930, Doolittle had left active military duty and joined Shell Oil Company as manager of its aviation department. He was not a desk man. He was a man who understood speed at a molecular level. And what he understood, with a clarity that eluded generals and politicians, was that the next war would be won not by the nation with the best airframes, but by the nation with the best fuel.
Doolittle began lobbying Shell executives to invest in producing 100-octane aviation gasoline. The response was polite disbelief. In the early 1930s, 100-octane fuel existed only in tiny laboratory quantities. Producing it commercially cost over $30 a gallon at a time when regular motor gasoline sold for less than 20 cents. There was no market. No engine in production required it. No Air Force in the world had specified it. Shell colleagues called his obsession Doolittle's million-dollar blunder. He kept pushing. He used his fame. He used his engineering credentials. He flew demonstration aircraft, burning the experimental fuel, and showed what the extra octane could do. The results were dramatic. Engines that had produced 600 horsepower on 87 octane could push past 1,000 on 100 octane without modification beyond adjusting the supercharger boost. The fuel did not just add a little more power, it transformed the aircraft. But Doolittle had a chicken-and-egg problem. Engine manufacturers would not build engines for a fuel that did not exist in commercial quantities. Oil companies would not invest in refineries for a fuel that no engine could burn. Someone had to break the cycle. Doolittle chose to break it from the fuel side. He convinced Shell to build the refining capacity first, betting that the engines would follow. Meanwhile, across the Atlantic, a French mechanical engineer named Eugene Jules Houdry was attacking the same problem from a completely different angle. Houdry was born in 1892 near Paris, the son of a wealthy steel manufacturer. He graduated first in his class from the École des Arts et Métiers, earned a gold medal from the French government, and captained his school's soccer team to the national championship. Then the Great War arrived. Houdry served as a lieutenant in the French Tank Corps and was seriously wounded at the Battle of Juvincourt in 1917, earning the Croix de Guerre for extraordinary heroism. After the war, Houdry became obsessed with engines, specifically with making them faster. He raced Bugattis and understood that the bottleneck was not the machinery, but the fuel. France had no oil. It had mountains of low-grade lignite coal. Houdry set up a laboratory to convert lignite into gasoline using catalysts, substances that accelerated chemical reactions without being consumed in the process. He built a demonstration plant in 1929 with French government funding. It worked. It also cost too much. The government pulled the money, the plant shut down. But Houdry had made a discovery that would change the war. He found that a naturally occurring clay called Fuller's earth, rich in silica and alumina, could crack heavy petroleum molecules into lighter ones. The lighter molecules had higher octane ratings. The process was not thermal cracking, which relied on brute force heat and produced low-quality gasoline with an octane rating around 72. Houdry's catalytic cracking produced gasoline with an octane rating of 81 to 88 from the same crude oil. It was a revolution in chemistry. But France did not want it. In 1930, Houdry packed his laboratory and moved to America. Vacuum Oil Company had heard about his work and invited him to Paulsboro, New Jersey. He formed the Houdry Process Corporation and began collaborating with Vacuum Oil and later Sun Oil Company. The work was painstaking. The catalyst worked brilliantly for a few hours and then died. Carbon deposits, a residue called coke, choked the active surface of the clay and shut the reaction down. Houdry diagnosed the problem and invented a regeneration cycle. You ran the reactor until the catalyst was fouled, then you stopped the oil flow, blasted the catalyst bed with hot air to burn off the coke, and started again. It was crude, it was a batch process, but it worked. In 1937, Sun Oil opened the first full-scale Houdry unit at its refinery in Marcus Hook, Pennsylvania. The results stunned the petroleum industry. 50% of the output was high-octane gasoline. The yield was nearly double what thermal cracking could achieve from the same barrel of crude. When Arthur Pugh Jr. of Sun Oil presented a paper on the process at the American Petroleum Institute in November 1938 at the Stevens Hotel in Chicago, the audience sat in silence for several seconds before erupting in applause. They knew what they were hearing. They were hearing the future of fuel. By 1937, Doolittle's lobbying had finally paid off. The U.S. Army Air Corps adopted 100 octane as its new standard fuel for combat aircraft. General Henry Hap Arnold, who had become Assistant Chief of the Air Corps, was a believer. Shell and Standard Oil of New Jersey won contracts to supply test quantities. The price plummeted. By 1938, 100-octane fuel cost 17.5 cents per gallon, down from $30 just 4 years earlier. The industrial machine was awakening. But awakening was not enough. In September 1939, Hitler invaded Poland. Britain and France declared war. The RAF was still running its Spitfires and Hurricanes on 87-octane fuel. They had been testing imported 100-octane from America since 1938, and the results were extraordinary. The Merlin engine, when tuned for 100 octane at 12 pounds of boost instead of 6 1/4, produced roughly 300 additional horsepower at low altitude. That translated into 25 more miles per hour at sea level and 34 more miles per hour at 10,000 feet. It also doubled the interval between engine overhauls from 500 hours to 1,000. The aircraft were the same, the fuel was different, and the difference was the gap between life and death. The British Air Ministry moved with uncharacteristic speed. By March 1940, every Spitfire and Hurricane in Fighter Command was being converted to 100 octane. The Merlin engines received modified supercharger settings and shrouded cylinder heads to handle the increased boost. The first tanker load of 100-octane fuel, designated BAM 100, had already arrived in Britain from Standard Oil's refinery in Aruba in June 1939. Stockpiling began immediately. When the Battle of Britain erupted in July 1940, the transformation was complete. The Spitfires that rose to meet the Luftwaffe over the Channel were not the same aircraft the Germans had dismissed over France. They were faster, they climbed harder, they could sustain combat power longer. The Merlin III engine, tuned for 100 octane at 12 pounds of boost, now produced 1,310 horsepower during emergency takeoff and climb. It was the same block of aluminum and steel, the same cylinders, the same crankshaft, the same supercharger housing, but the fuel flowing through the carburetor was a different substance entirely, and it unlocked a reservoir of power that had been sealed behind the wall of detonation physics. Luftwaffe pilots reported with confusion that the British fighters they had outperformed just weeks earlier were now matching or exceeding their speed. During the desperate summer of 1940, Bf-109 pilots who had entered combat expecting easy kills found themselves in even fights or worse. Spitfires that should have been slower were closing on them in dives. Hurricanes that should have been unable to climb were intercepting bombers at altitudes that had previously been safe. The German intelligence officers studied the wreckage of downed British fighters and found no new engine modifications, no secret supercharger, no hidden weapon. The airframes were identical to the ones they had fought over France. What they could not see, because it had already burned, was the fuel. The planes were the same, the fuel was not. The arithmetic was merciless. 13 points of octane, the difference between 87 and 100, translated into the margin between conquest and survival. A 1943 analysis by the Sacconi Vacuum Oil Company put it bluntly. It was an established fact that a difference of only 13 points in octane number made possible the defeat of the Luftwaffe by the RAF in the Battle of Britain. The Germans were burning B4 aviation gasoline with an octane rating of 87. They had nothing better. Their synthetic fuel program, built on coal hydrogenation plants operated by IG Farben, could not match what American catalytic crackers were pulling out of Venezuelan crude. But the crisis was far from over. The Battle of Britain was won, but the global war was expanding. America entered the conflict after Pearl Harbor in December 1941, and the demand for 100-octane fuel exploded beyond anything the existing refineries could supply. In 1940, American production of high-octane aviation gasoline stood at roughly 40,000 barrels per day. The military estimated it would need over 500,000 barrels per day by 1944. That was a 12-fold increase. And the Houdry process, brilliant as it was, had a fatal limitation. It was a batch operation. You could not run it continuously. Every time the catalyst fouled, you had to shut down, regenerate, and restart. It was like trying to fight a war with a rifle that needed to be cleaned after every third shot. Standard Oil of New Jersey saw the problem coming. In 1938, when the success of the Houdry process became impossible to ignore, Standard Oil assembled a consortium called Catalytic Research Associates. The members read like a roll call of global petroleum power. Standard Oil of New Jersey, Standard Oil of Indiana, Anglo-Iranian Oil, Royal Dutch Shell, the Texas Company, along with engineering firms M.W. Kellogg and Universal Oil Products. Even the German chemical giant IG Farben was initially involved, though they were dropped from the group in April 1940 for obvious reasons. The consortium's mission was blunt: develop a catalytic cracking process that did not infringe on Houdry's patents and that could run continuously. Two chemical engineering professors at MIT, Warren K. Lewis and Edwin R. Gilliland, proposed a radical idea. Instead of keeping the catalyst in a fixed bed and periodically stopping to regenerate it, what if you moved the catalyst itself? What if you ground it into a fine powder, suspended it in the stream of hot petroleum vapor, let it do its work, then separated it out and sent it to a separate regeneration vessel where the coke was burned off, all in a continuous loop? The catalyst would flow like a liquid, circulating endlessly between the reactor and the regenerator. They called it fluid catalytic cracking.
The concept was elegant. The engineering was nightmarish. Nobody had ever tried to circulate millions of pounds of fine powder through a continuous industrial process at high temperatures. The catalyst particles were microscopic. They eroded pipes. They clogged valves. They behaved unpredictably in ways that contradicted textbook fluid dynamics. 4 engineers at Standard Oil of New Jersey, Donald Campbell, Homer Martin, Eager Murphy, and Charles Tyson, led the effort to turn the theory into reality. They built a 100-barrel-per-day pilot plant at Standard Oil's Baton Rouge refinery in Louisiana. It began operation in May 1940. The pilot plant was a cathedral of controlled chaos. 15 stories of steel piping, reaction vessels, cyclone separators, and regeneration kilns, all connected in a loop that never stopped. The air around it smelled of hot metal, sulfur compounds, and the sharp chemical bite of hydrocarbon vapor. The heat was oppressive. Workers on the upper platforms could feel the reactor vessel radiating through their boots. The noise was a constant industrial roar, the rush of high-pressure steam, the whine of centrifugal compressors, the deep mechanical heartbeat of pumps pushing catalyst slurry through pipes that glowed dull red. The catalyst, a fine zeolite powder the color of pale sand, rose through the reactor in a column of hot vapor, cracking the heavy petroleum molecules as it went. The chemistry was violent. Long hydrocarbon chains, molecules with 15 or 20 carbon atoms, were ripped apart into shorter fragments with 5 or 8 carbons. These shorter molecules had higher octane ratings. They were the prize. At the top of the reactor, cyclone separators spun the spent catalyst out of the gas stream with centrifugal force. The catalyst, now coated in a black skin of carbon deposits, cascaded down through a standpipe into the regenerator, where blasts of hot air burned the coke off in a controlled inferno that reached 1,200 degrees Fahrenheit. The regenerated catalyst, now glowing faintly and stripped clean, flowed back to the bottom of the reactor to start the cycle again. It was a perpetual motion machine of chemistry, and against all reasonable expectations, it worked. The urgency was staggering. More than 1,000 technical experts across the consortium worked on the project simultaneously. It was later described as the greatest scientific effort directed to a single project before radar and the Manhattan Project. In a decision that captured the desperation of the moment, 32 commercial fluid catalytic cracking plants were authorized for construction before the first commercial unit had even started operating. Eager Murphy had concluded the process was sound based on the small-scale tests and was bold enough to proceed. The first commercial FCC unit, Model I, began processing 13,000 barrels of petroleum per day at the Baton Rouge refinery on May 25, 1942, just 5 months after Pearl Harbor. The results were transformative. FCC units could run 24 hours a day, 7 days a week without stopping. They produced vastly more high-octane gasoline per barrel of crude than any previous process. And they generated critical byproducts. Butadiene, one of the 2 essential components of synthetic rubber, poured out of the cracking process as a bonus. This was vital. Japan controlled 90% of the world's natural rubber supply. Without synthetic rubber from FCC byproducts, the American war machine would have ground to a halt on flat tires. By 1945, 34 FCC plants were operating across America. Combined with the Houdry fixed-bed units and other catalytic processes, they had increased American production of 100-octane aviation fuel by 6,000%. The United States was producing over 500,000 barrels per day. It supplied 85% of all Allied aviation fuel. The Soviet Air Force flew on American octane. The RAF flew on American octane. Every P-51 Mustang that escorted B-17 bombers over Berlin, every F-6H Hellcat that swept the Japanese from the Pacific sky, burned fuel that had been cracked in American refineries using a process invented by a Frenchman, championed by a daredevil, and industrialized by oil company engineers who had never fired a weapon in their lives. The refineries themselves became war zones of a different kind. They ran around the clock, 3 shifts a day, 7 days a week. The men and women who operated the cracking units worked in conditions that would horrify a modern safety inspector. The temperatures near the regenerator vessels could reach 140 degrees. The catalyst dust hung in the air like a fine, toxic fog. Pipe joints leaked hydrocarbon vapor that could ignite with a single spark. Explosions were not theoretical. They happened. Workers died. But the fuel kept flowing because everyone understood what was at stake. By the end of 1944, more than 4,000 women were working at Chevron's Richmond refinery alone, operating the control boards and monitoring the gauges that kept the cracking towers running. These were not Rosie the Riveters building airplanes. These were the invisible army that fed the invisible weapon. Nobody wrote songs about them, but every gallon of 100-octane that left their plants carried the heat of their labor inside it. The Germans never closed the gap. Their synthetic fuel program, dependent on coal hydrogenation, peaked at a B4 rating of 87-octane. Late in the war, they developed limited quantities of C3 fuel rated at 95-octane, but Allied bombing systematically destroyed the hydrogenation plants. Albert Speer, Hitler's Minister of Armaments, would later identify the bombing of the synthetic fuel plants as the decisive blow. By 1944, Luftwaffe pilots were rationed to minimal training hours because there was not enough fuel to let them practice. New pilots arrived at frontline squadrons with as few as 60 flight hours. They were lambs.
Meanwhile, American pilots trained extensively on abundant 100-octane, arriving at the front with hundreds of flight hours that their German counterparts could only dream of. The fuel gap was not just a performance gap, it was a training gap, a readiness gap, and ultimately a survival gap. Japan's situation was even more dire. Japanese aviation, the Germans never closed the gap. Their synthetic fuel program, dependent on coal hydrogenation, peaked at a B4 rating of 87 octane. Late in the war, they developed limited quantities of C3 fuel rated at 95 octane, but Allied bombing systematically destroyed the hydrogenation plants. Albert Speer, Hitler's Minister of Armaments, would later identify the bombing of the synthetic fuel plants as the decisive blow. By 1944, Luftwaffe pilots were rationed to minimal training hours because there was not enough fuel to let them practice. New pilots arrived at frontline squadrons with as few as 60 flight hours. They were lambs. Meanwhile, American pilots trained extensively on abundant 100-octane, arriving at the front with hundreds of flight hours that their German counterparts could only dream of. The fuel gap was not just a performance gap, it was a training gap, a readiness gap, and ultimately a survival gap. Japan's situation was even more dire. Japanese aviation fuel peaked at 87 octane. The Nakajima Homate engine, designed to produce 2,000 horsepower, had been engineered with the assumption that 100-octane fuel would be available. It never was. The engine never reached its design potential. Japanese engineers knew what 100-octane could do. Before the war, they had tested a Mitsubishi Kinsei engine on imported American high-octane fuel and watched it leap from 1,000 to 1,400 horsepower. But when the trade embargo cut off American fuel, that knowledge became a torment. They knew what they were missing. They could calculate exactly how much faster, how much higher, how much deadlier their aircraft could have been. The octane gap was not just a technical disadvantage. It was a strategic death sentence. Eugene Houdry never saw combat in the Second World War, but the war came for him anyway. When the Vichy government of Marshal Pétain collaborated with the Nazis, Houdry became president of the U.S. chapter of France Forever, an organization dedicated to supporting Charles de Gaulle and the Free French. On May 3, 1941, the Vichy regime revoked his French citizenship. Houdry became an American citizen in January 1942. His two sons, Jacques and Pierre, enlisted in the United States Army. The man who had fought for France in the trenches of 1917 now fought for the Allies from a laboratory in Pennsylvania, his catalyst cracking crude oil into the fuel that would liberate his homeland. After the war, the catalytic cracking revolution reshaped civilian life. The same processes that had produced 100-octane aviation fuel now produced higher-quality automotive gasoline, enabling the high-compression engines that powered the great American automobiles of the 1950s. The petroleum industry was permanently transformed. Every modern oil refinery on Earth uses a descendant of the fluid catalytic cracking process that was born in a desperate race to feed the engines of war. Houdry himself turned his attention to a new problem. The high-performance engines his fuel had made possible were now filling American cities with exhaust fumes. In the early 1950s, when the first studies of Los Angeles smog were published, Houdry founded a company called Oxy-Catalyst and began developing a device to clean automobile exhaust using the same principle that had cracked petroleum, catalysis. He patented the catalytic converter in 1956. It was an idea decades ahead of its time. The tetraethyl lead in gasoline poisoned any catalyst, making the device impractical. It would not become standard equipment until 1975, 13 years after Houdry's death. Jimmy Doolittle, of course, went back to war. He returned to active duty, led the famous raid on Tokyo that bears his name, commanded the 12th Air Force in North Africa, the 15th Air Force over the Mediterranean, and the 8th Air Force over Europe. After the war, the historian Walter Boyne wrote that Doolittle did more for the Allied effort as a scientist than as an airman because of his push for 100-octane fuel. The man they called a daredevil had saved more lives with a chemistry lecture than with a bomb. The story of 100-octane aviation fuel is not a story that fits neatly into a monument or a museum plaque. There is no statue of a catalytic cracking tower in Washington. No memorial wall lists the names of the chemists who figured out how to regenerate a fouled catalyst bed. But the numbers do not lie. The United States produced 600 million barrels of 100-octane aviation fuel during the war. 85% of all Allied aviation gasoline came from American refineries. The octane advantage gave Allied fighters a measurable edge in speed, climb rate, and operational ceiling over their Axis counterparts. The war was not won by fuel alone. It was won by soldiers who bled on beaches, by sailors who drowned in frozen seas, by pilots who burned in flaming cockpits. But every one of those pilots needed an engine that worked, and every one of those engines needed a fuel that would not detonate under pressure. The men who solved that problem did it not with courage under fire, but with courage under ridicule. Doolittle was laughed at for his million-dollar blunder. Houdry was abandoned by the French government and stripped of his citizenship. The engineers at Standard Oil bet the company's future on a process that had never been tested at commercial scale, authorizing 32 factories before the first one proved it could work. That is the hidden machinery of victory. Not the rifle, not the tank, not the bomber, but the invisible liquid in the fuel tank. The 13 points of octane that separated the Spitfire from the coffin, the refinery from the ruin, the free world from the dark.